Tonight's speaker is Dr. Umberto Berardi. Dr. Berardi is the director of the B-Top laboratory at Ryerson University. His main research interests are related to the study of new materials for improving performance within the built environment. His main focus is on phase change materials and aerogels. Dr. Berardi has published over 120 journal articles and 120 conference papers, receiving over 6,000 citations. He was recently proposed by Ryerson as the first ever Canadian research chair in building science. Dr. Berardi was the chair of the 2019 International Conference on Indoor Air Quality, Ventilation, and Energy Conservation in Buildings and the international chair of the Conference on Sustainable Design, Engineering, and Construction in both 2015 and 2016. Dr. Berardi is the editor-in-chief of the Journal of Canadian Acoustics, and he is a member of the editorial board of many other journals, including Energy and Buildings, Sustainable Cities and Society, Journal of Building Performance Simulation, and Building Simulation. Everyone, please join me in welcoming Dr. Umberto Berardi.
So, good evening to everybody. Thanks, Rob, for the introduction. Thanks to Haba, our president of OBEC, for inviting me tonight to give you kind of a 1 hour virtual seminar that, as you can find in the title, is going to be dealing with the variability of the thermal conductivity value. So the target of this seminar is to be, kind of combining research and pragmatic values for practitioners. So I'm going to actually try to give as much as possible in the next hour my point of view in terms of thermal conductivity, especially bringing up front a bit of the research we've been doing at Ryerson, really looking at the operational a lot of insulating materials and try to get a sense of the effective performance of these products. I moved to Canada 7 years ago, and since then I've been actually working quite a lot with companies and manufacture of a lot of insulating products. And really our interest has been over the last few years to get a sense of what a real insulating material is doing in field. So this is more or less actually our focus over the last few years, and this is what I'm going to try to speak about tonight. So a bit of the agenda of tonight's talk, I'm going to start giving you a bit of a refresh of the definition of thermal conductivity, just actually to give you the sense of how fuzzy sometimes this definition could be. I'm going to propose you a bit of an introduction to our standard measurements and, American standard as well as Canadian and international standard definition for measuring the thermal conductivity. And then I'm going to move on, 3 different aspects, which are going to be the effect of temperature on the properties of an insulating material, the effect of moisture content, and so how different relative humidity levels can actually influence the thermal conductivity of a lot of our products. And then finally, I'm going to focus on some challenges that can be related with the installation and field conditions that a lot of insulating products may have. And then finally, I'm going to recap in a summary at the end of our talk. So if you see at the bottom right of the presentation, you see some kind of 5 little dots, and those are going to be the outline, kind of bracket. So 1, 2, 3, 4, 5. So let's start actually. Why I selected thermal conductivity as the topic of this inaugural seminar? It's because probably as building scientists, thermal conductivity is the most important parameter in building science. We work mainly in getting a sense of thermal conductivity in envelopes, try to get the best products for the function we actually aim to do. And at the end of the day, although we don't realize, we run thermal conductivity analysis somehow for any building science simulation. And the different values that the thermal conductivity may have in practice, at the end of the day, may affect a lot of the performance of our buildings. When I'm speaking about performance, I'm speaking at the same time, not just of heat flux across the envelopes, but at the end of the day, I'm speaking about the entire capability of an envelope to secure occupant comfort, the entire actually energy demand of our buildings, questions related with condensation and risk of mold or any other deterioration of our enclosure. And so although often we look at thermal conductivity to met codes, and we use specs to kind of secure that our envelopes, our enclosure is code compliant, in reality, we often have to deal with many more things than a simple energy related aspect. So if you take a lot of international, kind of reports and standards and approaches, they typically tell you to design enclosure in order to meet the minimum required R value. And so often building scientists and envelope and enclosure specialists are basically selecting materials to put together different layers in order to get that minimum R value. And this is often done with an approach that we go for a spec and we find the theoretical performance of that product. So today's seminar is about, is that theoretical performance of a material corresponding to the reality, or how far it can be from the theoretical number. Now, assuming we were in a building science theory class, I would have started with this kind of slide. Thermal conductivity is, at the end of the day, is the rate of heat transfer that can occur in a unit of thickness of a material, or a unit of area, or a unit temperature difference. So very basically, the thermal conductivity tells us how much heat flux undergoes actually across the material. So it's basically a material property, or should be a material property. So we assume that different materials will have a different thermal conductivity. And we go to textbook, we go to library of software to get a sense of what is the value of thermal conductivity of each one of these products. We typically use kind of the value of thermal conductivity to separate what we consider a good insulating material from a poor insulating material. We define thermal bridges based on the fact that we can have different values of thermal conductivity of two materials that are side by side. And so the heat flux can find a short way to kind of pass our enclosure through a material that has a very high level of thermal conductivity. So a very high thermal conductivity creates an high way for heat flux to escape our enclosure. But let's actually step a bit back when we speak about heat transfer across the material. So thermodynamics tell us that every single time we have a temperature difference, we have a heat flux. And typically this heat flux always goes from the warm side to the cold side of the object. And we typically actually are assuming that the heat transfer can occur across different modes of heat transfer. We typically, and I'm going to really be quick, but I need actually to spend a couple of minutes to kind of recap a bit of thermodynamics to give the sense of this talk. We typically speak about the modes of heat flow in terms of conduction, convection, and radiation. And for those of you that do not necessarily remember clearly the difference between each one of these two kind of heat transfer modes, we speak about conduction as the heat transfer mode that prevailing in solid. We typically speak about convection as the fluid heat transfer mode, and radiation about the heat transfer that occurs in a void. Now, this very rough definition, I should say, are pretty wrong. And a lot of you may be surprised if I'm assuming that we are often underestimating the fact that heat transfer by conduction can also occur in a fluid, can occur in a liquid, it can occur in a gas. And that's exactly indirectly the focus of today's talk. So every single time we speak about enclosure, we pretend to kind of build together a lot of solid layers that next to each other are in contact to each other. Each one will have a kind of a thermal conductivity of each one of those materials. Each layer will have a thermal conductance. And then summing together the thermal resistance of each one of the layer, we will get the overall R value of our enclosure. So we pretend to think that in an enclosure, there is no convection or no radiation. Well, at least we dream this. Assuming there is no air infiltration across our enclosure, we tend to think that there isn't any kind of convection happening across our enclosure. At a microscale level, this is probably true. We probably do not have a lot of convection. But what happens at the microscale? Now, if at microscale you start looking at what an insulating material looks like, you start getting a sense that a lot of the insulating materials, if not all of them in reality, are full of voids. So they are typically actually characterized by a lot of voids where clearly there is a gas. And the gas actually moves, and the gas actually transfers heat through convection. Now, the presence of a void actually means that there is going to be radiation across the surface of a single cavity. So in reality, in each material, although we think there is just conduction, the more porous the material is, the more we're going to get convection and radiation. And insulating companies know this very well, and they try to work ways to kind of cut as much as possible heat transfer by convection and radiation that otherwise will occur also in an insulating material. So first of all, instead of speaking about a thermal conductivity as a property that is, just reflecting the heat transfer by conduction, we should probably start thinking about the apparent thermal conductivity as a better definition of a behavior of a layer that has been basically allowing heat flux mainly through conduction, but also it's going to allow some heat flux through convection and through radiation. So basically, we never have a single heat transfer mode isolated from the others. And especially in a porous material, we have a lot of the different heat transfer modes altogether. Now, let's go back to the definition. Why we're interested in thermal conductivity? We're interested in thermal conductivity because we design enclosure in order actually to limit as much as possible the heat flux across an enclosure. So basically, at the end of the day, the majority of enclosure design really involves selecting material with the K value in this formula, which is quite famous formula for thermodynamics that tells us that the more actually material is conductive, and when I'm saying the more is conductive means the K or the lambda is big, depending on the kind of book you have been using, the more you get actually a lot of heat flux. So we use materials that have often in building science a quite low thermal conductivity, so a quite low number of K, a quite low number of lambda, in order actually to limit as much as possible the heat transfer across our enclosure. So just to actually memorize and get a sense of these different ideas, assuming I have an enclosure that has 30 degrees on one side and 20 degrees on the other side. If this enclosure is full copper, which is clearly not a building enclosure, then it means because the copper is a poorly insulating material, it's actually quite conductive as a material, that the thermal conductivity, the lambda, is quite high, a few hundreds. And if you start getting silicon, this drops actually to 100, 150. And then, as you probably may memorize already at this point, we have a lot of materials that have a thermal conductivity in fraction of 1. Actually quite small fraction of 1. So the majority of the products we typically use for insulating our enclosure, it's often having a thermal conductivity in the range that is ranging from 0.05 to 0.1 watt meter Kelvin. So it's quite a low number. And more in the building sector, we are seeing a kind of an introduction of new products with thermal conductivity of 0.01. So we're getting actually to values that are extremely low, and the lower are these numbers, the more we need to be careful in trying to understand what that means, that very small number. Just actually to report again what I was saying in a kind of a more graphical sense, these are the thermal conductivity values of a few selected insulating materials we often use in buildings at the temperature of 25 Celsius. You see that we can have some fiberglass typically standing in the range of 0.04. We have a bit of actually highly insulating products these days getting to popularity, aerogel, vacuum insulating panel, all these kind of new materials with a thermal conductivity of below 0.02, and a lot of kind of wood materials in the range of 0.1. So this is more or less giving you a kind of the variety of these numbers. But I want you to pay attention for 1 second to the title of this graph. The title of this graph speaks about the thermal conductivity of a few materials at 25 Celsius. And this is going to be important in a moment once we start actually getting the sense of the spectrum. So a few minutes ago, I was mentioning the fact that in many insulating products, we have a lot of voids. And a lot of voids means there is going to be a gas. For some of these products, the gas is air. It can happen actually in a fiberglass or in a lot of open cell foams. For some other kind of materials, this gas can be, the ending phase of a blowing agent material. So imagine a lot of the closed cell polyurethane or, polyisocyanates. The gas is different from the air, and there is a reason for that. And we're going to see in a moment what is the reason for that. But what I want to focus on for 1 second is that imagine you have this kind of microscopic photo of a kind of a material. And this is the cross section of the material where you can see this bubble, which are the kind of empty cavity of the material. The material needs to be insulating. We all understand that a lot of the insulating materials means they have a very low density. They are kind of porous. They have a lot of these kind of cavities. And in the cavities, there is a gas, or in the best scenario, and typically this is not a scenario that we will deeply look at today, there could be some void. And what that means, it means that together with the solid polymer conduction of the heat transfer across the solid portion of the material, in the cavity, there is going to be a bit of conduction across the gas. There's going to be a bit of heat transfer by convection of that gas. There's going to be a bit of radiation in the cavities of that kind of little cavity and little porous. So all these kind of things are coupled together, and they are important to memorize. Just to give you a bit of a snapshot of this, so I'll give you the sense of the meat of the today class. I want to actually make sure that you get a sense of whenever we look at thermal conductivity of a foam, and for a foam at this point, I'm considering a closed cell foam, the reality is that the solid conduction on the polymer is typically between 5 and 40% of the overall thermal conductivity of that material. The rest of the thermal conductivity in that material is typically happening for gas conductivity. So there is a gas conductivity in it. There is also a bit of gas convection that can be so significant to become even 30 to 40% in terms of contribution of that material. So companies are constantly trying to figure out new ways to lower these numbers. And that's why we get new generation of foams. That's why we get new kind of vacuum product that are trying to get rid of a lot of those gas. But also this is why we need to pay attention to these new mechanisms. Because at the same time, they're trying to cut as much as possible in good faith, the gas conduction or the gas convection or the radiation inside the cavity. But as soon as those products lose some of these properties, so as soon as some of the gas escape or some, kind of other gases get into the material, then typically these high performance products tend to have a different effective behaviors from their theoretical number or from the lab values that we have been given in a technical sheet. So let's actually go back to what I was mentioning before when I was mentioning this Federal Trade Commission document that basically speaks about the trade regulation rule and how we need to kind of get always data from a technical sheet. And if you look at this document, and it's freely available online, if you actually Google it at the end of this talk, it's actually speaking about the fact that every single insulating product that we put into commerce, we need actually to make sure that we get a sense of the thermal conductivity. And it's also telling you a bit of the standard that we need to use to get this value. It speaks about the STM C177 or the STM C518. I'm going to mention in a moment what they are and what actually they represent. But basically, these are standardized way to help different labs across the globe to have a bit of reliance on same approaches to give you the thermal conductivity value of a product. Now, if you start Googling and you open those kind of standards, for example, they tell you that the test needs to be done at kind of a 75-degree Fahrenheit of average. So in the middle of the material, you need to have 75 Fahrenheit, and you need to have basically 50 Fahrenheit on one side, the cold side, and 100 Fahrenheit on the warm side. So cold side at 50 Fahrenheit, warm side at 100, 75 in the middle, and we try to establish in a lab a kind of homogeneous heat flux, unidirectional, across the material that is exposed to this 50-degree Fahrenheit difference. There are other standards that are using different temperature, but for now, let's actually focus on these numbers. So these numbers are the numbers that have been used, and if you actually want to do a conversion, you actually realize that testing a material between 50 and 100 Fahrenheit, it means to test a material with an average temperature of almost 24 Celsius, actually 23.8 Celsius. So in reality, in the lab, typically what we are doing, we are testing a material at a temperature where we probably do not need an insulating product. We are testing materials almost an environmental condition around 20 degrees, and nobody needs an insulating product at 20 degrees. We need insulation when our roof reaches minus 30 or when our roof reaches plus 50 degrees. We don't really need the material to insulate at all when the enclosure is around 20 Celsius. And I think here there is the secret of a bit of misinterpretation of what a technical sheet means. So in reality, all the heat flow or heat flux methods, depending if you're using a guarded hot plate or a kind of a heat flow meter, or even if you go for international standard 8301 that was firstly approved in 1991 and has been recently reapproved in 2019, in reality, all these measurements that are used to populate technical sheets give you values of thermal conductivity at the temperature that is the ambient temperature, which is a temperature that is probably not important for enclosure design. needed for air conditioning design. And in reality, there are a few standards that have highlighted this element. There are standards like the one that I'm reporting in this slide that have actually said, pay attention, you should probably start using thermal conductivity values at the effective temperature in which that material will be used in field. In other words, they're saying, although people do not necessarily know these kind of standards, that if you're using a material to kind of insulate a pipe and the pipe is going to be at 200 degrees Celsius, you probably should have tested the material at that temperature. If your roof is going to be at -40, it's probably getting a good effort if you're actually trying to understand what it means for a material to kind of insulate at -40 degrees Celsius. So first of all, let's get the sense of what do we do typically. A lot of companies come to our labs or comes actually to labs around the world. They bring actually a sample. The sample goes in a box like this one. And what actually means, it means that we establish a temperature difference, homogeneous, average in ambient condition, and not necessarily a good representation of what happens in the field. In the field, a lot of other things may happen. So previous standard I was mentioning before actually speaks about a few different temperatures which we should start populating technical sheets. So we all know this, we all understand that temperature may imply a different value, as well as a few other environmental factors I'm going to mention in a moment. Clearly, just actually to be honest, a lot of companies do not find interest in doing this kind of extra measurements. On one side, because often a lot of the software we use have no interest or capability to get the sense of thermal conductivity dependence on temperature, but also because nobody wants to start doing a lot of tests because they tend to be quite expensive at one point, and nobody wants to start doing a lot of tests unless everybody does those tests. And so far, basically, there is a general approach where doing the tests at only 20 Celsius is good enough actually to populate a technical sheet, to give a value to the industry, and the industry will start actually moving from there. So in reality, this is not necessarily the best approach, but it's been quite common, especially until recently, where doing this kind of tests was quite expensive. And now these kind of tests at different temperatures are getting more and more available across the globe. And so we are starting getting new technical sheets with thermal conductivity values in different conditions. So let me actually start telling you a bit of extra values in a lot of the experience that we have been having over the last decade or so in terms of thermal conductivity measurements. So first of all, we have actually realized that, well, materials are temperature sensitive. We tend to say this is not important, but we need to be carefully when we use the thermal conductivity as a fixed value to be aware if temperature has an impact on that material or not. We should actually more and more these days be paying a bit more extra attention to the homogeneity of a material. A lot of products are not homogeneous at all. You can take a technical sheet and not necessarily correspond to the kind of material you can have in field. A material should not store a lot of energy and should really store a lot of thermal energy, because otherwise that thermal conductivity is a kind of a misleading concept. And then last but not least, we need to actually start getting a sense of what is the importance of convection, macroscopic convection and microscopic convection. So convection within the cavity, but also convection around the material. And what happens, if the same layer is arranged in different ways, how much actually this changes the convection. We all understand that convection in a vertical cavity or in a horizontal cavity, it's affected by a different coefficient of Newton. What does it mean actually for the thermal conductivity? So I'm going to focus a bit on results to give a bit of actually data so you get the sense of it. I'm going to use actually, a bit of fiberglass, mineral wool, and a few foams in this seminar, so you can get a sense of the different, kind of materials. So the first element you need to actually start getting the sense of is that we typically want to have materials with a lot of porosity, a lot of voids, a lot of actually air or another blowing agent, another kind of gas. But we also need to pay attention to this. So you can have a material that is, quite full of voids, like a fiberglass, and a lot of voids and not really a lot of material. If you take actually a macroscopic photo of a fiberglass, you will really see that there is little material. And what it means when there is little material is that the air can move quite a lot. So convection in a fiberglass can be a significant element contributing to the overall thermal conductivity. That's why a lot of foam companies like this kind of cellular structure, where they try actually to close these cells. And as soon as we move from open cell to closed cell, these cavities get quite trapped. And so we have more and more material, few interconnected voids, a lot of surface area. And what it means that radiation becomes more important and convection becomes less important. And, recently we are getting new and new products, from open cell, we have moved to closed cell. And more recently, we have moved to new products like aerogel, where these cavities becomes extremely small. A lot of small cavity means convection will be almost stopped completely, and then there is going to be a bit of radiation that we need to start paying attention. So, on the left, you see what is typically happening on the, any foam materials, a kind of a closed cell foam. And then on the right, you see what's happening on an aerogel. So the aerogel prevents convection to occur, but actually still leaves some radiation component. And we need to get the sense of all these heat transfer in a solid material, for which often we think there is only conduction, but in reality, in the gas cavity of the product of this material, we also get a bit of convection and radiation at the same time. So let's actually, now that we have set the bar of the theory of thermal conductivity in insulating products and in porous products, let's start getting a sense of what happens in the field. Now, these are two photos that probably will tell you quite easily from the photo that probably these materials are not behaving as the technical sheet will have suggested. So the spec of these products was probably giving to the designer the thermal conductivity that was at least in order of magnitude lower from the thermal conductivity that these enclosures have encountered in the field. And in both cases here, a main concern is the fact that we get a lot of moisture and a lot of condensation. So in the field, the reality is that material is not as dry as companies bring to labs. When I receive in our lab materials to be tested, they are as warm as a kind of a new pizza. They are so coming out from an oven, and there isn't a little actual humidity. But in reality, a lot of our enclosure tend to have a lot of fluctuation in relative humidity. So moisture content gets trapped into the cavity. And for some of these products, they are closed cell. They tend to be kind of impermeable to moisture content, but that also means that once the moisture enters in those materials, then it gets trapped in those materials, and we need to pay attention to that. So first of all, temperature effects on thermal conductivity. In general sense, although we typically use constant thermal conductivity, I'm safely going to tell you today that every material will have at least a linear temperature-dependent loss. The linear temperature-dependent loss really is an effect of radiation. Higher temperature brings more radiation brings more thermal conductivity. So typically, a safe assumption could be to use a dependency in the range of 0.0002 part meter Kelvin per Kelvin. So this tells you that a material at high temperature will conduct more, a low temperature will conduct less. If you are designing for Yellowknife and you don't consider this low, that's probably not a bad idea, because you're basically underestimating the real thermal conductivity of a product. I mean, Yellowknife will be more insulating. So at the end of the day, it's not a big deal. But if you are designing for a hot climate, or if you are designing for a roof in the middle of the summer and there is a lot of solar radiation, do not avoid to consider linear temperature-dependent lows. And these temperature-dependent lows, it can be a bit bigger for a material like a polyethylene, around 0.003 or 4, and a bit less for polystyrene. And we don't have time to understand why, but there is actually a low, and it's easy to find this low. And a lot of software these days are starting implementing this function. So you're going to start getting more and more software where there is basically the opportunity to say, oh, click, temperature-dependent thermal conductivity low accepted. So this is a graph that has been around for 15 years, so quite old, but gives you a snapshot of the temperature effect on thermal conductivity. So you see there are some products that have a curve that is a bit more flat, other is a bit kind of more significant, but all the products, especially mineral and fiberglass, have a linear dependent curve. Period. This curve is real. If you're only designing an enclosure to be in the middle of Washington, D.C., probably your fluctuation is not significant. Probably your kind of analysis will not be affected by big error. But if you're designing for conditions that are quite different from 20 Celsius, then the error may become bigger. Just to give you the sense, we have run actually over the last 4 years this project where we have analyzed a lot of different foams to get the sense of this. And I'm actually going to say, do not consider the photos. I took these photos of these 4 materials out of Google early today. So these kind of 4 photos are not the real material I'm showing you, but these are actually some of the results we obtained for fiberglass, rock wool, XPS, and a bit of foams. And what actually we have found? We have found that, XPS, rock wool, fiberglass have a pretty linear behaviors. Polyisochannel tend to have a bit less actually linear behavior, or tend to have a non-linear behavior in a temperature below 0. I'm going to spend a bit of time, but I don't want you to focus too much on the values, but I want you to focus on another aspect. And the aspect is that whenever we take measurements at 20 or 23, 24 Celsius, we are not necessarily taking a good photograph of the behaviors of a material in field. When I mean in field, it means that these products are going to be kind of affected by temperature quite a lot. Just to give you the sense, this is actually true for every material. We did the test for aerogel plaster, blankets, same story. The reality is, the more dense a material is, the less important is the temperature. So when you start adding materials that are packed together, then temperature is not any more important because porosity is not any more important. So just to give you the sense, all these kind of plaster in the yellow, green, orange line, they were full of aerogel. The aerogel was filling the cavity, and then the thermal conductivity was almost independent from the temperature. These are a few blankets, same story. These are tests done from minus 10 Celsius to plus 60, more or less actually same behavior. But with foams, it's a bit different. With foams, we get these kind of inverting behaviors. And I don't have actually time to discuss too much about why this is happening. But what actually is quite clear for a lot of people is that a lot of these foams have, kind of gases, or some of the foams, especially, old generation of polyisochannel. Okay, so this is not necessarily a problem that you find in any of the new products. It's often a problem that you find consistently when your roofs, they were built, a decade ago, for example, and some of the new polyisochannel may still have this trouble. And the trouble is basically that some of the blowing agent we have been using, at the end of the day, they are trying actually to condense. When they condense, there are actually 2 phenomena that are happening all together. On one side, we get a liquid into the cavity, in the microcavity of the foam. But more importantly, when you start actually getting some condensation, you start getting basically a lower pressure of the gas. So the gas is rare and can start moving more. So convection starts being more significant than otherwise you will have if all the gas was remaining in the gas form. So just to give you the sense of the effect of temperature, very quickly, I'm going to show you, kind of a lightweight frame construction in terms of wall and roofs. And we actually did a bit of measurements. We did a bit of simulation. So just to give you the sense, here you see, for example, the temperature fluctuation basically across 1 week. You see a week in January and you see a week in August. So temperature goes up and down, and so clearly thermal conductivity goes up and down. If you see the y-axis, you see that the number is not really changing too much. So often this is not necessarily a big problem, temperature in isolation, when you look at fiberglass, or when you look at rock wool, or when you look at XPS. So there is a fluctuation in thermal conductivity because clearly the temperature changes. But in reality, the fluctuation doesn't really generate a huge difference in terms of its flux. And more importantly, typically in Toronto, winter and summer tends to kind of overall compensate each other. So you get more flux in summer, a bit less flux in winter. You sum up all together this construction, and you more or less get the same kind of situation. Although this is still critical because you need to get a sense of condensation risk. So, here you can see, and I'm happy at the end of today's talk to kind of give you a bit of PDFs to look at these results. But I'll move on to the second element that is quite important too, and it's the element that deals with the content of moisture in the material. Now, clearly, the more you get moisture into the material, the more you get actually highly thermal conductive material. And this is pretty clear. And none of the material that we can use in the construction sector will always stay, dry. They always are going to be experiencing a lot of, high relative humidity levels. They're going to get some moisture, and they get actually with moisture and higher thermal conductivity. Higher thermal conductivity will bring actually more heat flux and likely cool down those products and likely generate more condensation risk. So this is actually kind of a second order risk that can become quite significant for a lot of products. So we did the same kind of experiment I was telling you before, testing a lot of different foams, polyurethane, polyisocyanurate for different kind of relative humidity levels. We brought in climate chamber, left the material for months, tested after a month of exposure at that relative humidity. And you can get the sense of the importance that, for example, moisture can play in an open cell form, and typically does not play in a kind of a closed cell form. But a closed cell form still will, with the time, absorb a lot of moisture. So you need to pay attention to the fact that that moisture will not escape easily. So it doesn't get absorbed a lot, but then when it gets absorbed, it retains there for quite significant good amount of time. And here you see a bit of these kind of results. We also have been testing products in terms of how the thermal conductivity of a material changes by the time the material ages. And so what it means ages, for people working quite a lot with foams, they may be aware of the fact that we have standards to look at the long-term thermal resistance. The foam industry doesn't like this kind of approach because forces foam industry to look at the long-term behaviors versus a lot of other insulating companies. They only tell you the product behaviors when they're in the factory. They don't tell actually you what happens to a fiberglass, kind of years after, or they don't really have any obligation to tell you those kind of things. But the reality is, with the time, a material tends to be more thermally conductive. I'm going to show you in a moment why that's the case. So first of all, at the end of these kind of long multi-year projects, we have been able to generate for a lot of products, and really, really a lot of products, 3D shapes of thermal conductivity in the z-axis in this graph versus relative humidity and versus temperature. What that means, it means that in a lot of kind of a decade ago simulation, thermal conductivity was flat, was a constant. Thermal conductivity of a closed cell polyurethane, it will be a number like 0.03 bar meter Kelvin. But in reality, a product tends to be, like a polyurethane tends to be more thermally conductive at high temperature, less thermally conductive at low temperature. And when it comes actually to relative humidity and moisture content implication, it tends to kind of have a Gaussian distribution when at one point it starts to kind of absorb a lot of moisture and try to kind of a thermal conductivity that becomes quite higher. So we also look at a different generation of foams to get the sense of what actually has been happening in the foam industry. And we don't have actually that much time to look at this. But if I want to give you one of actually snapshot, is that you need to pay some attention when you use polyisocyanurate at extremely cold condition, in condition where you can expect a lot of high relative humidity. These products are great. We use probably in the 50% of the entire North America roofing sector, but once they get exposed to significant cold temperature, and so do not really always trust what happens in American reports. Canadian climates can be quite tougher and quite more critical in terms of cold temperature values. And whenever actually you get also high relative humidity, now these products are exceptionally good at ambient temperature, so extremely insulating at 20 Celsius. They may diverge quite a lot from the value you find in a technical sheet. And just to give you the sense, you can see in the Z of this graph, you can actually probably have a material that doesn't behave as a 0.02 in thermal conductivity, but behaves as a 0.04. So, you're effectively having half of the thickness of that material in terms of performance. So we have generated these reports with a lot of products, a lot of 3D curves, and we have also, also run simulation. Now, just to give you the sense of this simulation, what we have been doing is, try to get the sense once we combine temperature and relative humidity, what happens to the thermal conductivity of those products in the real field. And we have done simulation and we have done measurements in long multi-year campaigns of different walls and roofs. So just to give you the sense of what's happening, I'm going to show you, for example, a wall. You see, an insulation on the exterior side. It's a foam insulation, 5 centimeter of foam insulation. You see in the graph the temperature that you can actually see in terms of July and January. And here it comes actually what happens, for example, to the thermal conductivity. Now, to give you the sense of what's happening is that you can probably see there is a continuous blue line. That's the thermal conductivity of material in the center. And the two dotted lines above and below are the thermal conductivity of the two circles that you find, more exterior towards the sheeting or more towards the interior side of the wall. So this gives you the fluctuation of the thermal conductivity across the entire thickness of this foam. And we've been doing this in many cities and some monitoring, not just with polyisocyanurate, but also with polyurethane, open cell, closed cell. You can see, for example, here the oscillation of the thermal conductivity as it goes up and down in the bottom line of these kind of two figures. You see the continuous red line going up and down, oscillating around 0.045, but also getting sometimes values higher around 0.05, sometimes lower value around 0.04. And as soon as we went actually into the July, we ended having a lot of times actually values around 0.035. Same story with polyisocyanurate, but the reality is that with this product, the oscillation becomes quite bigger, quite more significant, quite more actually important to take into account, into consideration. So you need to pay attention to these kind of things because often, we tend to underestimate and we often actually do not consider that much the aging of these products. And the fact that, materials tend to have an aging that, especially in foams, can be quite significant, but it's also happening in fiberglass and in mineral wool. And in a second, I'm going to show you what that means. This kind of aging occurs because the gas escapes, moisture enters, it gets trapped, and it changes the gas, basically balance within the porosity of any insulating product. Once you get moisture content into the material, then the moisture stays there for quite a significant amount of time. And we've been doing a lot of work also trying to understand how long it takes to kind of escape for a moisture, how long it takes for a blowing agent to escape from a foam, and how we can get a sense of, what is going to be the long-term behaviors of these products 10, 15, 20 years from now. Now, pay attention that with buildings, reality is that we are building this construction and, we know that they're going to stay there for decades. So this is not just an academia problem. This is something that speaks about real sustainability and real performance 30 years from now when that building will still be there. Now I'm going to focus towards the end of the presentation on two different aspects. The first one is the importance of how do we install the insulation, what it means the thermal conductivity once the material is installed. So these are two buildings not too far from Ryerson. We are on College and Carlton and Young. These two buildings, were installed in good faith. People were putting so many fastening. I really have no idea what it means, the thermal conductivity of this mineral wall. This is quite problematic more and more these days that we go up. And in the field, people are putting more and more fastening. What is really the thermal conductivity of this? And what can happen, for example, and this is another installation that we did with aerogel blankets, when we use highest performing materials and we basically attach to the real wall with a glue, with different kind of sealing, or with some kind of fastening on plastic. Now, I don't have time, but I want actually to give you a snapshot of the result of this investigation. What you can see here is an investigation done in a lab where we basically compared, just putting glue, putting fastening that were plastic, putting fastening that were different kind of steel. And so here you see the different kind of markers. And on the x-axis of this graph, you see the number of anchors per square meter. So if you remember the two photos of Toronto downtown buildings, they were typically in the range of over 10 fastening for a single square meter, okay? That means that basically the thermal conductivity, when it becomes the equivalent thermal conductivity in the field, becomes completely, kind of different from the theoretical technical sheet. So somebody could say, okay, Umberto is suggesting us, not to put a lot of fastening. That's not necessarily the truth, because as soon as you don't put fastening, what you start having is, a lot of airflow around insulation. Airflow, at the edge of the insulation, but also airflow within the insulation. More airflow means more conduction. More conduction means more effective thermal conductivity. So although, in the previous part of this presentation and this seminar I was telling you that, you need to pay attention to the foam industry because foam sometimes behaves differently in the field from what actually was happening in the lab. In reality, a lot of mineral walls suffer these kind of problems much more than, their corresponding foam materials, because really airflow around materials, when the materials is, kind of represented by fibers, and there is not really that much material, then airflow can be quite significant. And airflow can be so significant to kind of fully decrementally generate a result of thermal conductivity that is quite significant. Now, this is not new science, to be honest with you. Mark Bomber, some of you may have encountered him, already spoke about this in the 70s and then in the 80s. And, in 2003, he made this publication, which I often suggest my students to get and read. And at one point he said, basically, we know this, and we have been knowing this for, decades. At the end of the day, it's just a matter of going to the field and making sure that the insulation, and I'm not even speaking about thermal bridging, I'm speaking about the fact that the insulation needs to have a given thickness that is homogeneously the same and doesn't need to be compressed towards the edge of the insulating product. In good faith, we often do this. We're trying to squeeze actually a lot of insulation, but that insulation squeeze can actually generate a lot of voids, and a lot of those voids will generate a lot of air cavity movement, and that air cavity movement will generate more convection. So I'm going to actually turn towards the end, and I want actually to kind of summarize a bit what I've been discussing over the last 40 minutes and giving time for question. But in summary, I will say thermal conductivity does not depend only on thermal conduction. You need to pay attention to conditions that may generate convection and radiation as much as possible. You need to actually get the sense that temperature may have a significant influence. And the more actually you're insulating something that is hot, the more important it is. But if you're using some kind of foams, also the colder the condition of operation of the material is, the more actually you can have a thermal conductivity quite different from the nominal value. So, in reality, you need to start paying attention across the year, and you need to start getting a bit of better sense of dynamic variation of the thermal conductivity. Just to give you the sense, a lot of software these days are automatically starting giving you input to facilitate this process. What we are still missing is a full understanding of the behaviors of a lot of these products in conditions that are different from the standard, different from the 20 Celsius degree. We also need to start getting a better understanding that once moisture gets into the material, thermal conductivity becomes higher. And so there is no point in doing a glass air analysis just to get the sense of, okay, I'm getting, no glass air, no condensation risk. If I'm actually closer to a 90% relative humidity, there is a lot of moisture in that product. That moisture generates a higher thermal conductivity of that product than I'm expecting. And higher thermal conductivity will mean, at the end of the day, that material will allow an high heat flux. And if that was a thermal bridge, it's likely the case that a higher heat flux will also correspond to a higher chance of condensation. So moisture should be, more and more part of our analysis. It shouldn't be considered a separate factor as an on-off that only occurs when condensation is happening. We also need to start paying attention at the technology we have been using. One of the things that I've been surprised at recently is that a lot of super insulating products, such as aerogel products, a lot of polyisocyanurate, they're starting being advertised with thermal conductivity values measured at 0 Celsius. Now, this is a bit of a game, fake news, I should say, because you're starting getting a thermal conductivity at 0 Celsius, where a lot of other products have been getting thermal conductivity values at 20 Celsius. And if they were, not necessarily declaring those kind of things, then you start getting different values of thermal conductivity. And this can actually represent a bit of a questioning mark for the value that we find in technical shift. We also need to start getting a better understanding of the fact that the material ages and buildings are built for decades. They're not built for the first day. So a bit of conscious analysis of how sensitive that material can be for an aging, is probably, a good strategy for the resilience of the construction. we need actually to start getting a sense of how we control the airflow within the material, but also around the material. And we need to actually design details to avoid, gaps and edge effect that could actually generate more convection. And then last but not least, we need to probably start getting a sense of how we install these products in the field. If you put actually products and you constantly penetrate with a lot of fastening, then at the end of the day, the thermal conductivity of any layer you can use will be super far from the nominal value you may actually have obtained in a technical ship. So just to give you the sense, I'm reporting here a bit of references. These are mainly papers published over the last couple of years that will give you a bit of the sense of the work done at Ryerson University in the BTOP lab. You can see that there are some papers that speak about fiberglass and mineral wool. Some other papers speaks about the aerogel. Some of papers speaks about polyurethane and polyisocyanurate. So they actually have we'll say, comprehensive series of analysis of the implication of effective thermal conductivity for the vast majority of the insulating products you may actually have encountered so far. And without further ado, I want actually to thank Chris Schumacher and Rocky Boyer for the useful discussion we had over the last few years on these topics. A bit of the kind of the funding agency for a lot of the work, and more importantly, the students that often do a lot of the data elaboration for the figures we have seen in today's seminar. Thank you for your attention.
Okay, thank you, Dr. Berardi. Hopefully everyone can hear me. We have a couple of questions that have come through. The first one is fairly lengthy, and I apologize for all the acronyms, but here it goes. It is well known that polyiso made with, oh, my screen just moved, sorry. It is well known that polyiso made with pentane have significantly reduced thermal resistance at lower temperatures. Have you tested spray urethane foam using HFC or the newer HFO, low global warming potential blowing agent? I would expect the HFC foam using HFC would be similar to XPS since it also uses the HFC blowing agent.
Yep. So, okay, let me actually clarify. So I don't want to enter today in a battle among companies or, different sectors, but I actually can, provide an answer to this question. So typically, I should say, I need to admit that even in our analysis, a lot of the polyisocyanurate experience some extremely low temperature, significant increase in thermal conductivity. So they tend to be probably among the best products at room temperature, but quite significantly deteriorating at extremely low temperature. And I don't want actually to open that, but the question speaks about the difference between the third and the fourth generation of polyurethane. So what happened in the polyurethane industry, just for those in line that they don't have actually a clear picture of it, the foam industry for polyurethane went from CFC to HCFC, and then HFC, and these days is going to the fourth generation of HFO blowing agent. So we have done tests with them, and I need to confess that both HFO and HFC, so both the fourth and the third generation of the blowing agents are quite okay. They don't have a significant decremental factor of thermal conductivity at low temperature. They tend to follow a straight linear relationship with a trend that is typically around 0.0015 watt-meter Kelvin. So it's also not only linear, so not significant lower temperature problem, but also is not really increasing too much at high temperature. So I mean, these two problems tend to be solved. Now, clearly, a lot of these polyurethanes still have, a nominal value of thermal conductivity that is higher than the value that you may find in some polyisocyanurate. So if I need to, just make a comparison, I would say a technical sheet will often speak about in favor of some of the polyisocyanurate, but an extremely low temperature analysis will probably speak a bit more in favor of third and fourth generation of polyurethane.
Okay, great. We'll move on to the next question. Regarding bad insulation, how does compressing the edges create more voids? It would be intuitive that it means less voids.
Yeah, so let's put it creates less voids for sure in the within the structure of the material. But what happens on the edge, it's not known. And even when you compress, more, in reality, you are generating a material that has an higher density, so has less voids, and so it generates more thermal conduction for the conduction portion. So the thermal conductivity tends to increase because locally, at that point, the material is denser. We all understand that conduction on its own, as one of the three heat transfer modes, becomes more significant when the material is denser. That's why metals are, more thermally conductive than insulating products. So, I mean, once we start basically compressing too much the material, then you start getting a higher local density that generates more conduction. So basically, it's hard to say because this requires, it's hard also to control this compression in the field. And it's, it never was done in a very systematic way, the control of the density in the field. But the reality is that in a very, easy to understand way, the condition in which we test materials in a lab can be quite different in terms of density for a lot of these losing products such as fiberglass from the condition in terms of thickness that they may end up having in the field. And often people do not realize this. Often people have no control of this because they not necessarily are tracking the way in which a fiberglass was compressed.
Okay, great. One other question. Is it worth it to have a similar study on timber and timber-based insulation materials like wood fiber in terms of variation of thermal conductivity?
I mean, like if the scope is to populate database to have the results for all the products, then I will assume yes. Every product should be fairly, assessed according to the same rules. And I'm a good advocate of moving away from single value of thermal conductivity and starting getting at least some data about temperature and moisture content impacts of these kind of things. Now, on one side, I'm expecting that wood materials will have less of these problems because their density is higher. And so as the density is higher, conduction as a heat transfer mode is more significant than conduction and radiation in these products. So in a wood product, often, the implication of the convection of air in the microcavity of the wood will be probably quite less significant than what is currently happening in some of the foam. And definitely a wood insulating board will not have the low temperature issue of blowing agent, condensating or escaping or so on and so forth. So I may expect that these problems may have less of an impact. However, clearly there is a demand for almost any product to be started evaluating in a different way. Now, on the other side, while a lot of these wood-based insulation boards and also a lot of other sustainable products may suffer less temperature, they probably would suffer more for moisture content. And here you also start seeing why a lot of companies are not interested in very comprehensive analysis, because they are, sometimes they are good for some properties and for some conditions, and they may probably not perform that well in other conditions. So once you start doing a very deep analysis of all the possible conditions, then each material probably will have some cost.
Okay, great. The last question I have right now is just a general question about if this presentation will be available as a download link, PDF, or video. I believe the presentation is being recorded and should be available on our website to the members, as our other presentations are. Unless I am wrong, I believe that it will be accessible through our website. Okay. With that, I'd like to once again thank Dr. Berardi for a fantastic presentation this evening, and I'd like to thank everyone for attending. Please keep an eye out for news on our next webinar, which will be held in June. Until then, stay safe and be well. Good night.